Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be focusing a lot on various phase changes with a specific focus in on how much energy does it take to do these phase changes. One of the reasons why we're so concerned about energy is this tells us a lot about stability of bonds, who's more stable, who's less stable, but in a practical sense, it does take energy to change phases, but sometimes you get energy right back out. So let's go ahead and look at one of the more important phase changes we haven't talked about so far, and that's melting. However, because chemists are chemists and we have a very old nomenclature, this is also sometimes called fusion. I know it seems a little bit odd, but fusion can represent the melting of a substance. And then in the reverse direction, we have freezing. So melting and fusion both indicate going from solid to liquid. Freezing indicates going from liquid to solid. So when we're looking at how much energy it takes to do a process, it will take energy to break a solid lattice to form a liquid because we're breaking apart these good intermolecular forces. And the energy required is called the enthalpy of fusion. Now, one of the cool features about trying to break up a solid is that unlike a gas where as soon as you have a liquid, you have some gas. When you have a solid, you don't always have a liquid. And as a result, most of the time, you just have either a solid or a liquid. Now, one of the cool parts is that melting almost always occurs at a single temperature. This is what makes the melting point so cool. If I have a solid and liquid present, and assuming I don't have too much contaminants, you're always going to be at the melting point of that substance. So if you have pure water and pure ice, no dirt, no salt, you can pretty much tell exactly what temperature it's at. 32 degrees Fahrenheit, 0 degrees C. Now, what we can do is use this to help identify both the melting point and the enthalpy of fusion. So we saw this a little bit last semester in lab, where we did a melting point of alum. If you had pure alum, what you would see is that as we added heat, it would slowly increase at a fairly constant rate, and then it would stay at a given temperature for a while as you go from solid to liquid, because it takes some amount of energy to do this process. And then once you're entirely liquid, the temp will end up increasing again. So what ends up happening is what we can do is evaluate how much heat it takes to require each of these processes. So we've already looked at essentially heating of liquids and solids. We can predict the amount of energy it takes using the heat capacity and the change in temperature. However, going from solid to liquid, well, this can be predicted using that enthalpy of fusion. This will tell you how much energy it takes to relate 1 mole of the solid to go from 1 mole of solid to 1 mole of liquid. And at that point, you're just staying at that same melting point until all of the solid has disappeared. So what we can do is use the same sort of ideas to try and encompass all of our 6 major types of phase changes. Yes, there are 6 major types. So melting or fusion is going from solid to liquid. We've already encountered vaporization, which is liquid to gas. It will also have its own energy, which we've encountered so far, enthalpy of vaporization. We have condensation. So think about water condensing on your windshield or making dew. And then we've got freezing, good old liquid to solid. However, there's 2 other processes that you might not be quite as familiar with. Sublimation, which is going directly from a solid to a gas, and deposition, which is going from a gas to a solid. And these are probably, again, the least familiar to you in terms of terms, but they're probably quite familiar to you if you look around the everyday world. So usually when we think about sublimation and deposition, what we tend to think about is things like frost on your windshield. So when it gets cold enough, if I have too much water in the atmosphere, it won't form dew on the grass. It will form frost on the grass. It will go straight from water vapor to solid and making beautiful crystals along the way. Same thing happens on your windshield. So it isn't enough for it to just be very cold to form frost. It also needs to have enough humidity, enough water in the air to form the frost. Either humidity or temperature, both are not alone. You'll need both, to make deposition occur. We also have things like sublimation, which often occurs when you think about things like dry ice. So this is solid CO2. You expose it to air and it will immediately produce CO2 gas. And along the way, it often forces water vapor in the air to deposit on the surrounding surfaces because, again, there's enough vapor in the air and it's cold enough. However, if I want to try and figure out the energy required for sublimation, so again, going from solid to gas, this will just simply be the enthalpy of fusion plus the enthalpy of vaporization. So remember, enthalpy is a state function. So if I go from going from a solid to a liquid and then a liquid to the gas is the same thing as going directly from liquid to gas in terms of enthalpy. Now, in order to get the enthalpy of deposition, you just take the sublimation number and reverse it, put a negative sign. So sublimation requires energy and deposition produces it. However, there turns out to be one last phase that you're probably not quite as familiar with, and this is called a supercritical fluid. So this is a very kind of unusual form of matter, and it only occurs really under extreme conditions. You need both very high pressures and very high temperatures. So a way to think about this is if I increase the pressure, what we tend to do is favor very high concentrations, because again, pressure relates to concentration. As the pressure goes up, the substance will become much more condensed. Higher concentrations, higher molarity, that's going to favor a liquid. Liquids are high concentration substances. However, if you increase the temperature, this gives each of those molecules enough energy that it's moving around very fast, and that tends to favor a gas. Now, something really kind of interesting happens. If I increase both the temperature and the pressure high enough, what ends up happening is the substance wants to be very concentrated, but it wants to move like a gas. And so I take these two separate liquid and gas phases and they merge to become a single new phase. This is called our supercritical fluid. Now, a very important part about a supercritical fluid, you need to be above a certain temperature called the critical temperature and above a certain pressure called the critical pressure. It isn't enough to be above either one or the other. You need to be above both at once. And a good way to think about this is that these supercritical fluids, they pretty much have the density or the concentration of a liquid, but they flow a lot more like a gas. And as a result, they're used in a lot of very cool applications. So one great example is dry cleaning. So if you have supercritical CO2, CO2 is a nonpolar molecule, so this would generate a nonpolar fluid. However, it turns out that CO2 really isn't usually dense enough to be used as a cleaning fluid. However, what happens is if you put it as a supercritical fluid, it has these high concentrations, and because of its nonpolar nature, it can start picking up dirt and grease off of clothes without exposing your clothes to, say, water or soap. So if you have clothing like silk or satins that are very vulnerable to water, it gives you a way to remove stains without ever exposing them to water. This is dry cleaning. And a very similar process, if you ever drink decaffeinated coffee, what you often do is you run supercritical CO2 over the coffee beans, and it picks up a lot of nonpolar molecules. The one we usually care about the most is caffeine. So caffeine gets pulled up into that supercritical fluid and runs off very nicely. And so even though it does seem like a weird phase of matter, we do actually run into the implications of supercritical fluids all the time, even if we don't see them on a daily basis. So next time, we're going to be taking all of these various phase changes and all of these various phases of matter and try to predict at what temperatures and pressures any given one of them will occur and when they will transform into each other as we talk about phase diagrams. Until then, take care.